Hello, everyone. Welcome to this session. So we are excited to bring you some of the latest work that we have been doing on AI accelerators as part of the ALCF AI testbed. So how we'll run this session is, so I'll have some overview slides that I will walk through. So we kind of show the AI testbed, what systems do we got, and some of the current work that we have been doing. And following that, so we'll also have a hands-on session on two systems primarily. So I just pulled up my slides here. So as you've known by now, so Argonne has a history of deploying diverse hardwares for its computing infrastructure, all the way from IBM machines like Interpret Mira to Theta GPU, and more recently Aurora. As you have seen, just the scale and the diversity in the hardware was the key two factors for expanding our portfolio. And around 2020 timeframe, so that's when the non-traditional hardware chips kind of started emerging, and so we started to look into those systems to understand how capable they are and what kind of workloads do they support. And this is kind of complementary to the supercomputing resources that we already provide. And that's how we started the AI Testbed Center. It's kind of um, a small scale deployments of these systems. So we do a lot of testing initially, and we kind of make sure if they are really powerful and good machines. So our users, the domain scientists, everyone can use. So we kind of deploy them and make them available as production resources. So one of the key reason for doing this is, as you have known, so we have a lot of science based applications running on our machines. For example, there's some experimental facility that's doing actual experiments, and this computing facility, maybe it's crunching the numbers or it's doing some modeling work. So we wanted to see how these AI accelerators, so these are kind of purpose built to accelerate the AI workloads. So how can these two be working in tandem to cater to different applications like our simulations or data-driven models? And so that started with the AI test bed. So as I mentioned, this is the infrastructure for the state-of-the-art hardware accelerators, and they are different from what capabilities they offer, both from hardware and software perspective. The goal here is to have this testbed as a platform to evaluate the usability and the performance of these systems for a wide variety of applications. It's also critical for us to understand how these machines can be integrated to our existing supercomputers. So there's a lot of work that's happening, and in the AI test bed, so we do rigorous benchmarking, performance analysis, and also port various science codes on these systems. So currently we have deployments from Cerebrus CS3, Sambonova SN30 and SN40L. We have a Grok rack. We have a graph core machine, and pretty soon we're also putting up a 10 torrent machine. Again, the systems that we got support training and inference. Like few run both, few are maybe Grok and SN40L are primarily for inference. Cerebrus currently runs training. It's also will support inference going soon. And so the main goal is to uh, see or kind of run the different workloads on these machines. Yeah, so as I mentioned, so the SN Sambanov SN30, so we have the accelerator is called an RDU, so reconfigurable data flow unit. We have around 64 RDUs, and Cerebrus, we have got four wafer scale engines. The CS3 is the latest generation of their chip. For inference, we have from Sambanova the Metis cluster, which is the SN40L hardware platform. And we have two nodes of 16 RDUs of SN40L series. We also have Grok rack. The chip is called as a Grok chip. And for running kind of a traditional HPC kernels, Cerebrus and Tenstorrent, they can also kind of provide some support. As I mentioned, these systems are up in the production at Argonne, and is available for anyone who is doing open science research. So 10 torrent will be coming up pretty soon, the next few weeks or so. So it's a quick high-level summary of the hardware diversity of this machine. So if you look here, so here we are capturing some of the parameters such as the compute units or the on-chip memory, the software support stack or the interconnects, and that gives a picture of how different each system is. For example, the Cerebrus CS3 cluster, the compute units are around 900K cores. It's a big, massive wafer, and on the wafer, it has almost 900K compute elements cores, which very very powerful chip, and also it has a pretty high on-chip SRAM, like 44 gigs of SRAM. So it kind of helps in having faster access to the memory as well. For example, if you also look at the Sambonova machine, so per accelerator, there is a massive memory availability, or it's 1 or 1.5 terabytes. SN30 has one, and SN40L has 1.5 terabytes. So what this enables is catering to maybe larger models, or from the inputs, or the whatever inputs that you're doing, if they're able to fit on the memory. Um, and in terms of the software stack, each system has their own custom software stack. For example, Cerebrus CS3 and it runs on top of PyTorch. The Samba Nova has Samba Flow, and for inference, they use Samba Stack. Grok has their own custom inference engine, and but it can also support standard Onyx-based Linux. Graph core system also has, say, supports like TensorFlow and PyTorch. So if you see this table, right, so it shows each system is totally unique. So some has a huge compute, others has high on-chip memory. Now, that kind of provides a very interesting opportunity to cater to different applications. So first, what's kind of how different these are. So these systems kind of broadly can classify as data flow architectures. So if you look at this image, now for example, this is a standard simple model. On the GPU side, traditionally what we do is these kernels, they are launched one by one, and there is some kind of an overhead between the host and device. There are some optimizations that can be made with some, like, say, kernel fusing and other compare optimizations to minimize that overhead, but that's the way it's usually done. So the data flow way is a little different. It's called a spatial mapping. So here the chip is divided into a bunch of, like, compute and memory units which are interleaved, and the application which is running, it's kind of mapped onto this chip accordingly. So it kind of helps in mitigating the memory traffic movement and any associated overhead. So this kind of helps in accelerating the application much faster. So again, this is kind of a similar figure. So the left here shows the Sambanova architecture, where each accelerator is composed of different tiles, and each tile has a set of compute and memory units, PCU and PMU. The data flows across these units here. The compute happens, and the memory is stored on these memory units. On the right side here, we see a similar pattern for the Cerebrus wafer. So here the compute cores are called as Ps, or processing elements, and data moves across these processing elements. So the any hosted device copies are kind of minimized or mitigated, and the kernels which are mapped to these chips run much faster. So let's go into more details of each of these chips. So the latest Sambanova chip is called as SN40L. It's a reconfigurable data flow unit. So what does it means is, as I mentioned, it has the compute and memory units, and how they are mapped to kernels, so they can be changed based on the application and the mapping. It's not kind of a fixed mapping. So it is characterized by a three-tier memory hierarchy. There is an on-chip SRAM, which kind of helps in high-speed inferencing. It also has a HBM. It kind of helps to switch between different models when we are serving in for inference. And in addition, there is a 1.5 terabyte high capacity DDR memory. So this helps in holding these models in memory, kind of caters to supporting much complex models. As I mentioned, SN40L is right now for supporting inference-based workloads. So that's with a single chip. Now we talk about the node. It's called SN40L16. We have two of those. Again, each system, each of these RDUs are connected like all to all. And across the node, there is a 12 terabytes of memory. And again, there's a high bandwidth memory capacity as well. Again, there's a server which connects to all 16 RDUs and how do they communicate. And we have two of these nodes deployed. So we have like 32 SN40Ls in the Metis cluster. Next, going to the Cerebrus wafer. So we started with the early deployments, and again, now we have upgraded the machines recently to the latest generation wafer scale Engine 3. Um, so this is composed of 900K compute cores and 44 gigs of on-chip memory. So this picture, it shows actually the physical dimensions of comparing a Cerebrus wafer scale 3 series with say an NVIDIA GPU. So it shows like given the massive space available on the chip, it can accommodate much large number of compute cores, and that kind of helps in running these applications faster. The other key benefits of Cerebrus is the compute is kind of decoupled with memory, and models are run in a data parallel implementation. And there are some flexibilities where the external memory can be added independently of compute. Um, so that kind of helps in accommodating massive model sizes. Now, how this is done is through this cluster. So here, this picture shows this is called as an appliance mode. If you see, there are a bunch of nodes. So they are input pre-processing nodes for streaming the data. And for the additional memory, so there are dedicated nodes called memory X nodes. So these nodes store and stream the model weights. So how the training is done is all the weights are stored on memory X and they're kind of streamed layer by layer onto the wafer, and the actual computations are running on the wafer. And SwarmX is where it's those nodes are used for any broadcasts or any reduce operations. That kind of helps in scaling from say 1 to 4 CS3s. So this is the way that we typically the cluster is deployed here. Now again, a quick snapshot of the Graphcore Bow Port 64 system. So this chip is called as IPU, Intelligence Processing Unit. It's kind of a massively parallel MIMD based architecture. The main goal here is to again have a similar architecture what we've seen before. It's kind of the chip is composed of compute and memory units, and the data and the model are tightly coupled in this distributed SRAM. And we have this configuration which totally is composed of 64 IPUs. Again, the Grok chip. So we have a deployment for Grok rack, which are like 72 Grok chips. So again, each chip architecture looks something like this. So there's a dedicated compute engines for matrix multiplications or vector units, and dedicated work for dedicated chips for catering to different kernels. So the other key thing for Grok is it is only the on-chip. It's a SRAM only based device, and the placement of the or the mapping is again predetermined. So it's kind of they call it as deterministic computing, um, and this kind of built from a chip level to a Grok rack that's currently deployed. So, in terms of the tools that are available, so as I mentioned, each system has their own software stack to run different models. Again, to kind of measure how these workloads are running and trying to get some more details of the utilization and other parameters. So we have some tools which are available on all these machines. So these tools kind of help figure out if the model is running to the best possible way, or are there any other missing optimizations. So this Cerebrus has its own tool, and Sambonova has Samba Tune, and GraphCode has other tools as required. So we also do a lot of tutorials like this, and all the sessions which are available on the link provided here. So those sessions we do it annually, and they're more, it's a two-day deep dive session. So we do a lot of in-depth overview, and how to take a existing model, how to port them onto the software, and how to run them, and how do we do say performance profiling and tuning best practices. So we do cover a lot of those in the training workshops, and all the presentation recording slides are all available on that link. And for those who are attending SC next week, so we are also conducting a tutorial on Sunday. This is a 3 or 4 hour tutorial session. We have also are partnering with our vendors from Cerebrus, Sambanova, Grok. Again, it'll be more detailed than what we are doing today. So if you are at SC, I would recommend you to join this tutorial. As I mentioned, so the systems are also available for allocations. So one way to get SIST access is something called as a ALCF Director's Discretionary Allocation. You have this allocation request form. Basically, you give details on, say, what's the application is, what's the model or the data set, and there's a pretty quick turnaround time, and you get hours on the systems that you can use. As part of the NSF NAIR program, we also support or provide these resources. For the Sambonova Metis cluster, the SN40L, this is available for all Argon users via the inference service endpoints. I'm sure there was this inference endpoints covered maybe last week or the week before. So as part of that, we provide services on using the SN40L system too. And the documentation is available on this portal. There are a bunch of examples like how to log onto the machine, how to set up the software environment. There's some sample codes that you can try. We'll walk through in the hands-on session shortly. So maybe I can give a quick update on some of the science use cases that have been run on these on these systems. And again, the models are kind of totally diverse. So instead of like standard, say using standard models, again, there are kind of custom models that have been used in different science disciplines. Like there's a gene based model for protein synthesis. There are weather forecasting, drug discovery, diffraction imaging with cosmology. Um, Maybe I can show you one or two of those. So this application is called GenSLM. It's a genome scale language model. The goal of this application is to identify kind of what are the emerging variants of pandemic causing viruses, and identifying the mutations which are of concern. So the underlying methodology here is to adapt an large language model to learn this evolution. Those models are pre-trained, and they are ranging from 25 million to 25 billion parameters. The models are run on the A100s, NVIDIA A100 GPUs, Cerebras CS2, and the Sambanova SN30. So GenSLM was a recipient of the ACM Gordon Bell Special Prize for high performance computing-based COVID-19 research. So, so one overall summary for this application is looking at this performance comparison. Here we are looking at the 13B model training performance. If you're looking at the throughput, so we see an improvement of 8.5x on the Sambano SN30 compared to NVIDIA A100s, and also the 25x throughput performance gains compared to the Cerebras CS2. There was also a limited study done on how energy efficient these are. Again, they have proven to be pretty good in getting the energy efficient runs. Again, for the Cerebrus case, so we only used less than half of the entire wafer. So this example shows if you are kind of porting your existing models or any science application, so they are you can refactor the code, you can port them onto these machines, and we can expect to see good performance gains. this is an example for the accelerating a drug design problem. Here we are comparing the Polaris runs, which is A100s, and Grok. Again, this is kind of an inference-based application. The application code, the inputs are again kind of smiles representation for molecules. If you see this speed up plot here, see the because it's an inference-based application, porting this model to Grok and running them actually has gained significant speed up compared to the Polaris, which is A100 system. So again, this is an application for weather forecasting. So some of the key benefits of porting them to the Sambonova machine, as I mentioned, is the large memory capacity. So this kind of helps in training on high dimensional data. So here if you see there are the layers here, and there are a bunch of optimizations that are also happening across the Sambonova RDUs, and that kind of helps in accommodating much larger data sets. So this plot here, if you're looking at the sequence length uh, for the A100s, it's kind of limited by the memory capacity, but on the Sambonova machines, it's able to cater to much larger sequence lengths. Um, So this is an example for the diffraction imaging. Here we are looking at a case where with the materials, right? So it's kind of an X-ray imaging, and though once the materials is scanned here, it kind of generates multiple images, and they're kind of trained. And again, there's kind of having a live inference, which kind of predicting or kind of reconstructing the images. With the advanced photon source, which was upgraded, so the amount of data that's being generated has increased in both in the volume and in the resolution. For example, in one application, say today, um, the data set is in maybe 256 to 512 cube arrays. But again, with this latest upgrade, so we will seeing the data has gone up to 2K to 5K cubed FFTs. So to cater to this much larger volume and high resolution data sets, so we need to have a capacity, for example, on the Sambonova that can actually we're able to fit, and we're able to do this applications running on those machines. Yeah, probably I'll go to the next one. Yeah, so some of the key observations that we found out was, as I mentioned, each system is different. It kind of helps in having more compute and also kind of catering to much larger resolution data. Uh, Examples I've also shown, they are like energy efficient too, and it's also important for supporting low latency and critical applications. So some of the room for improvements is the porting efforts. So if an application is you want to like port them onto one of these machines, so there could be some refactoring because the software stack is a bit different. So maybe you have to rewrite with certain APIs and kind of optimizing them. So that can take some effort. And again, in terms of the performance analysis tools and debuggers, we have pretty good support. But again, this look, we need more coverage, and there's still room for improvement. As I mentioned, the if your user wants to run, say, a traditional HPC kernel, like a Monte Carlo simulation or FFT kernels, currently Cerebrus has a software framework called CSL that can be used to run that kernel on the actual wafer. Um, but again, there's work in progress to improve coverage. Um, Yeah, so that's a brief overview of the systems. But again, I wanted to keep it short, just giving a high-level overview of the software and the hardware and some key use cases. So now we'll go to the hands-on part. Varuni will be driving the hands-on part. Here we'll be looking primarily at the Cerebrus CS3 for training example, and we'll be using the Sambonova Metis cluster for inference.
Before we pop over, there were a couple of questions in Slack that I think maybe you could get to.
Okay.
One was asking about whether the lower layer docs are available for grok, such as ISAs. And this was someone who said they'd already looked at the ALCF docs and looked on the webs but couldn't find anything. Can you speak to
Uh,
that?
I am not sure if we have those talks, but I can check with the Grok team and I can get back to you, certainly.
Cool. And then one more question. Can you speak to like the current state of the test beds and whether they're going to be, are they going to be considered test beds for the foreseeable future? If there are any plans for large scale deployment or maybe larger scale deployment than where we're at right now?
So for example, the Cerebrus is we started with one IBIS CS1, I guess, and we are at four CS3. So technically, we are increasing the scale of the systems. Um, but yeah, so the test bed again, as I mentioned, we are also working with other vendors too. So hopefully, we are expanding the portfolio of machines. Um, but yeah, so this is pretty interesting on this machine. So we have upgraded the machines to the state-of-the-art latest generation hardware, and we also increased the scale of the resources.
And also at this point, they're almost all of them are accessible to essentially any ALCF user who wants to get on them, right? You'd submit for a DD or for an air proposal, and you will be able to access
Yeah.
essentially all of the things that you just talked through, right? Cool. Okay. Well, thank you so much. I will keep an eye on other questions.
Sure.
But for now, I will hand it over to Varun.
Thanks, Murli, and thanks, Paige. Am I audible to everyone? Okay. So first of all, Murli covered the first part of the lecture today. He went through all the details about what a data flow architecture looks like and why these AI accelerators are required and how they are different when compared to the traditional computing like the CPUs and the GPUs. So in this part of the lecture, we'll shift gears a bit and concentrate on the Cerebrus CS3 machine for training and the Sambanova SN40L for the inference. These are some of the most state-of-the-art systems today, at least in the AI accelerator space. So we'll actually get onto these systems and walk through how does it or what is the look and feel of accessing these accelerators and how to run your workloads, be it training or inference, and essentially how do you take a AI workload and run it on or evaluate on these systems. So all these information are available on the AI student science training series with the under the AI testbeds repo. So you can access any of them, and you also have the slides just, that was presented by Murli. So getting on to the hands-on part, let's start with the Cerebrus system. So as discussed, this is how a Cerebrus cluster looks like. So Cerebrus is the wafer scale engine, which is the actual compute unit of this entire cluster is like located here. Like and we have here at ANL, we have four of these CS3s. So depending on the number of CS3s we have equivalent number of the other parts of the cluster that was already discussed, but just for convenience sake, we go through it, and mostly these are these input pre-processing worker nodes, which are essentially kind of important for streaming your input to your actual compute unit, which are your CS3s. Apart from that, you also have a memory X and a swarm X. Memory X are essentially kind of servers that store your weights and stream layer by layer onto the wafer scale engine, including the input, and the computation happens, and the activations are stored onto the wafer scale engine, but and so on and so forth. So it happens layer by layer or a bunch of layers put together. When you are using these CS3s in parallel, in a data parallel mode, then the SwarmX comes into the picture. Of course, this is used only for the training mode, and which is helpful, kind of broadcasting your weights, and also doing the all reduce at the end of this training step. So any of the data flow architecture machines have like two steps when you really want to run any workload. So one would be the compile step, and the second would be the actual training or evaluation of it. So the compile step is where you actually, you know, bring up the graph and like produce all the artifacts, the compile artifacts that are required to actually fabricate, to program your fabric. And once that is done, you can run your workloads blazing fast. So if whenever you actually run or training, especially on these Cerebras system, you will kind of notice where is the when the compile happens. And usually the compile happens on these activation servers that you see, along with the management node that will facilitate in these compile jobs. The compile jobs do not interfere in whatever is running on the compute, which is the CS3s. So yeah, you can independently actually compile a model. And then once the fabric is available, or your CS3s are available, your jobs get kind of scheduled. So giving that a look, we can also see how to actually connect. And before this, we also, like Murli suggested earlier, all these informations are also available on our website, which is the ALCF website, which has under the AI test beds part. So when you log on to the system, you first have your local machine, and where you SSH to the login nodes. And from the login nodes, you have two possible user nodes, so you can use either one of them. You basically hop on to your user nodes, and then which kind of connects to the management node. So any of your jobs that you schedule on this user node, but ultimately that will initiate a Kubernetes cluster, which will schedule your job, and then that's how you kind of talk to the management node and the other CS3s that are embedded. So technically, the one that we saw earlier, which is this thing. This is somewhere kind of like sits over here. Okay, so having said that, so the best way to SSH is like, I'll kind of open a terminal and kind of walk you through how to do it. So everyone who have access to the ALCF AI testbeds should obviously need an ALCF user name. And then from your local machine, you can always log into the Cerebrus login node. So usually you use your, the mobile pass plus to generate the password, and then key it in. But I guess I've already logged in, so it didn't ask me. But here is where you actually log on to the user node, which I'm using the user node 2 to log in to the system. So this is essentially where you will now work on any of the commands. So all these information, of course, are always available in this particular repo. So the main job when you go onto the system is to kind of first clone the repository. So if you see, this is the Cerebrus model zoo repository that's publicly available from the Cerebrus. So currently it is at 2.7, but internally we have at 2.6. Um, so yeah, so essentially you operate using this kind of framework, and um, and yeah, so the first thing that you kind of do is to create a um, first clone the repository, which I will do uh, as part of AI series. And sorry. If anyone have access to the system, they can always follow along with me. So that it's kind of easier for you to go through the process as well. So yeah, essentially I just kind of git clone this, um, and then I just check out um, the 2.6, because that is the version that is compatible with the with all the software stack of the cluster that we have currently at ANN. Yeah, over the time, we usually upgrade it to the latest one, which happens whenever there is a new release on the plate. So this is how you first clone the repository. And the next important part is to create an environment which you can work with. So essentially, you create a um, Python virtual environment using these steps above as described. Um, and then all you essentially do is to pip install this particular model zoo that we just downloaded. So this kind of downloads all the required packages. I guess the PyTorch version that is adapted for this particular Cerebrus stack is around 2.4 or 2.5, if I'm not wrong. It, of course, it's a bit older version when compared to whatever the nightly build usually you get for PyTorch. But yeah, the software stack is kind of more matured with the older PyTorch version. Just a reminder, the Cerebrus, the virtual environment might be a bit huge when compared to other virtual environments. So ensure you have enough disk space while you operate. So this kind of takes a bit of time. While this is happening, we can just kind of take a look at uh, some of the commands that come handy while operating on Cerebrus. I think the one and only command we probably might need to kind of see what's happening and what kind of jobs are getting initiated and or what is running is the CSCTL. It kind of gives all the information for like both jobs, or it can even give about the cluster that you want. So if you have a system, um, so if you use just this CTL, it'll kind of give you what is the job name, then what is the phase it is at, and also which machine it's taken up, and also who is kind of running, and it essentially gives you all the information. Uh, Looks like somebody is trying out the system, which is great. So do let us know how you fare on that, and if at all you encounter any issues. So, like you see, the virtual environment is almost kind of done. Um, so Yeah, so every job that runs on this Kubernetes cluster will have an associated kind of ID or name or whatever you want to call it as. So this is called as a wafer scale job. And you can always like use that to kill or even like evaluate what is happening. Uh, yeah, you have more information on the CSCTL, and of course you can use our public website to find more information. So as part of this lecture, let's go through like how you run a Llama 2 7 billion example. So as I said, the model zoo is the go-to part for Cerebrus. There are a bunch of models that are there, and you can see um, when you go to the models, they're under multimodal, NLP, vision. They're different models. And of course, you can see even in NLP, there are a bunch of models, including the llama types, the MOEs, then you have the DPOs, some RL frameworks over there, and some old BERT or Bloom kind of models. But of course, you can, so all of these are essentially mostly transformer based. And probably you can kind of change the configuration based on your requirement, and you can come up with your own kind of custom model. So this is kind of done. So all you have to, for you to run the, um, sorry, so it's for you to run the Llama 2 7 billion example, we just go to the models NLP Llama. And then we've already activated the environment kind of here. So then what you do is essentially you kind of copy this YAML file. So this YAML file is what will define the configuration for your job that you're running. And if we kind of take a look at the any YAML file will kind of broadly look the same, right? So all your trainer arguments, including what kind of backend. So for NVIDIA, it would be CUDA, but for Cerebrus, it's the CSX. And you have the model directory, the model name, and all the model configurations that you are used to for a given transformer kind of architecture model, where you have the decoder layers or the attention part. Everything that's specific to the model is defined over here. So if you want to, if you want a model like Llama, but kind of want to play around with the parameters, all you do is change these parameters and run, and you'll have your own custom based model. Similarly, you have all the optimizer configurations, precisions that you want to set, and the training loop, like how many steps do you want to run this for, and everything that you have. Of course, you also provide the data for this, and the data is for easier sake, it's provided under the software data sets. Usually you can look for these well-known wiki data sets under this particular directory. So that's how essentially a YAML file looks like for any of the models that you will see. All you do now is to use the CSZooFit. This is just a wrapper that will initiate a Python script. And then you can just train your model for this particular model here. Uh, but of course, it kind of takes time. So I'll just go through how it looks like. So this is where we created the environment, and then this is where we provide the CSO kind of uh, uh, command. And like you'll see, so the first step would be to kind of like, of course, it'll kind of see whether you have a previous checkpoint that is available. If yes, then it'll restart from there, um, depending on the number of steps you have specified. So from there, it kind of starts, and the first part of it is like compiling the model. Here, before it wasn't compiled, so you don't have the compile artifacts that is associated with the model. So it'll first start compiling the model. And you can see base that this is the job ID that is associated with this compile of this model. And there'll be like, you need all the clusters or parts of the cluster that does the compile. So it obviously has to coordinate with all the Kubernetes pods over there. Um, and then kind of you can also use Grafana for kind of like reviewing how the job is progressing, and that's what is being told in the logs. Uh, of course, then you can also see that the compile is done. There will be an associated kind of tag with it. And then you can see that the compile is successful. So this is the first step. And once the compile is successful, you will see that the um, the cluster, which is the actual wafer scale engine, which is the WCSE in this particular case, will be programmed using this compile artifact. And then it'll initiate another job, which is your running your actual training loop. And you can see that it is preparing to use just one CSX. If you want to do use this multiple CSX, which we obviously have, you can just change the YAML file to include more than one CSX. And that will shard your inputs so that you can do a data parallel training. So then you'll see that it starts sending the initial weights like we discussed. It's a weight streaming mode where your training happens. So you'll see the weights being transferred. Then you'll see that the device is, completed programming the device, and then your input workers start streaming in your data. And that's where your apply staging is kind of complete, and then is where your CSX like training starts. So if you see here, I just use like 200 iterations, and then yeah, you with a log frequency of 50. So that's how you see, and and it'll provide you the input. Also save the checkpoint for you, as well as describe what's the throughput you get from the training. So this is pretty much how you train any model on the CSX. You can like use your own configurations to do that. So before I switch gears to Samanova, if anyone have questions, I'm happy to take on Cerebrus.
Yeah, we have one question in the chat. Well, we have two, which was answered. So maybe I'll speak to the first one. So someone asked, could you give a sense of like the model scales we're training on Cerebrus at performance GPU clusters? And Murali had answered that this trend, you see the trend for models ranging from billion to a couple hundreds of billion parameters for folks who didn't see that question. But there is one unanswered question right now. Someone asked, how do you ensure the accuracy of the model implementations on these accelerators? Can we do something with output bitwise comparison with NVIDIA GPUs? How can you trust the proprietary implementation parts on these models?
I mean, you can definitely take the losses that you get for each of these, and also the output. So you can definitely compare one-on-one for both of them. So I don't think that's, but again, like most of these models are, some of the models, especially if you see the inference based models, right, the weights are just kind of taken sometimes off the shelf, whatever you get, say from Llama 7 billion. But you can use the same checkpoint to be loaded onto these implementations of a different stack, right? So yeah, you can definitely compare, and of course, all these accelerators use kind of BF16. Some of them also use mixed precision. But again, there will be different precisions based on what you're using, and what you have used on NVIDIA when you compare also do matter at the end of the day. But we've seen it's pretty close. So
Excellent. I think we can jump to Salvador.
okay. So yeah, the second system that we have is Samba Nova SN40L, which we call Metis. And we have two racks of that, each of them having 16 RDUs. And this is a inference only cluster, but you can also do some fine tuning of models, but primarily we have used these for inference access. There are two ways kind of to use Metis. One using the web UI, and the other is using the API access. So for the web UI, probably this was also covered maybe like the last or the couple of weeks back. So Sambanova SN40L is embedded and is part of the infrastructure that is provided with the inference web services at ALCF. So you use the same kind of interface to kind of log in. Um, and like you see, oh gosh. So yeah, I'll have to re-log in. Give me a second. So yeah, this is a very if you encounter this problem, the way to go about this is so okay. So again, for Samnova, just to before I get into it, so for Metis, again, you have the information here on SN40L, the Metis. So yeah, it essentially has the same information. So the way you create, you can also use it using the API access, as I told, which you can create an Conda environment and install this Globus SDK. You use the Globus authentication for all the authentication purposes. So for this authentication, in case you encounter a problem like this, what you do is use first log out of all your Globus, and then you from the environment where you have initiated this global SDK, just use this forcibly to regenerate your token, and then use this to kind of get the new token. Make sure you're authenticating as part of your ALCF or ANL uh, account, the one that you have. And then you get access into, so you get a authentication code and you kind of authenticate it. So just to make sure that it kind of works, what we can do is check. So you get the access token using this file, and then just to see what kind of models are being served on Metis at this point of time, we can use this curl querying. And then you can see that you have the Llama 4 Maverick, and you also have the GPT OSs. So we have two racks. Each of the models take up the entire 16 RDUs. And then, so we have two models that are associated with each of the racks. There is also a possibility to bundle different models. We do have that support as well. So in case you want a different model that's not there as part of this list, like say a Llama 7 billion or 8 billion or 70 billion, or a Quen model or an other embedding model, do reach out to us. We will be able to help you serve a different model. So this is how you actually authenticate and see what's the list of models. So once you do that, you're always, be able to use this ALCF kind of account. And if I don't know what's wrong with this. Okay, I don't know. Maybe we'll come back to this later, but this is how it kind of looks like. It looks like a chat bot for you, like how you use a chat GPT, for example. OpenAI compatible API is what these systems use as well, or the interface uses. So you'll kind of like be able to select either the models that you're able to access, and then you'll get the chat kind of interface where you can use. So I'll leave that to you as part of maybe the homework exercises. But again, maybe we can go through one of these examples as to how to use the API access to kind of get the prompts running. So this model is kind of using the GPT OSs. So you just have to provide the kind of prompt and the model that you want. And of course, you know that you're using the Metis for the API. And then these are just what you need, and you can see that you got your response from your model. You can do the same. You can use either the curl command, or you can also use the Python interface where you use the OpenAI SDK. I have the same thing in Python in the test.py. So you should essentially get the same answer the other way around as well. So do try with different prompts and different models. Yeah. So these are it'll have a probably different kind of output here, just in terms of how you display it. But yeah, essentially it's the same. Yeah, that kind of covers most part of the exercises. Uh, Here I also want to like take you through that all the documentation. This is the ALCF public facing documentation, which I kind of went through in brief. And Cerebrus public facing documentation on training is available here, and the Sambanova document on inference is also available. Again, you can, so by the way, for Sambanova SN40L, since it's part of the inference cluster, you don't need any special access to access them. It's already part of the inference. So you would need only your ALCF authentication login to have access to this machine. But apart from that, the Cerebrus and the other systems do need the director's discretionary allocation. So you can use this website to apply for the discretion. You can get some node hours on these, and you can. This is mostly if you want to like explore these systems in depth, and you really want to run a large scale runs on these systems. So as part of their homework exercises, This here we list what's the homework for Cerebrus and Sambanova. It's pretty simple. Try to run the Llama 7 billion example that we went through, and for maybe different batch sizes and comparing the performance. That'll give you a good idea as to how how these systems are useful for like really large batch sizes. And also you can use a data parallel mode so that you can use more CSX and see whether you get a linear scale out. And then for Samanova, you can use your choice of your Hugging Face data set, and then compare the GPT OSS performance using both the Metis and Sophia. You can always use the LCF docs for any information. Most of the informations are present over there. And then otherwise write to us if you have any questions, slack us. I'm sure we'll be able to reach out to you. That pretty much concludes what I have.